Welcome everyone to this episode of Clearly Conveying. We're going to jump right back into our discussion on drive slip. Today we're going to discuss the intricacies of belt tension.
Every conveyor with a friction drive, you need a certain amount of T2 tension or slack side tension to make that actually move the belt and not just sit there and spin and slip. So by increasing that load or your T2 tension, you increase the pressure on that pulley, and just like on an automobile or a car, if you have more weight, it's going to have more traction and you're going to be able to go further or handle more load without slipping your tires, or in this case slipping your pulley.
Yeah, that's a great analogy, that helps people better understand, why they throw sandbags in the back of their truck, if the roads are icy.
More weight.
Yeah, more weight.
Exactly.
So with that, this is one of the most common areas where customers can manipulate things on an existing conveyor that they're having drive slippage issues, or where they're having drive slippage issues. Some of the more common things that we see out in the industry is, well, we need to increase the tension, the belt tension, and when that happens, it largely depends on the type of conveyor that you're using. What are some of the things that you have to be careful about with regards to if you're using a screw take-up type conveyor, where you're using manual take-ups to provide your tension, and you're having slippage issues, versus, for example, maybe an automatic take-up where you have a gravity take-up that's freely floating? Can you share with us some of the differences there?
Let's start with maybe just a couple of design assumptions when they're designing the conveyor. So a manual take-up, the basic definition is you're moving the pulley back to a fixed place, and that pulley does not move anymore. So when you start running the conveyor and you pull a lot of horsepower, your belt is basically like a big rubber band, and it's going to stretch to a certain degree. So on the carrying side, where you're pulling all that load, you're going to get stretch. And then on the return side or the slack side, that is actually going to start to sag a little bit, and the tension in the belt is going to drop there. And the difficulty with the manual take-up is if that slack side gets too low of tension, then you'll slip your drive. So people...
So if I may just try to illustrate that in a way that I can understand a little better. So when you put your conveyor under load with these manual take-ups, obviously it's pulling harder because you have more weight on the belt, and the belt's going to stretch.
Yes.
But because your take-up pulley is in a fixed position, it's not doing anything with that stretch, so you increase the sag. Correct. Which could potentially cause drive slippage.
Exactly. And in some conveyors, you can actually see that in the return belt. You can see the sag increase between your idlers. So now to go to the other side, what designers will do on larger conveyors, more complicated conveyors, they will switch over to some version of an automatic take-up, and there the design is, let's make that pulley move, so when that belt stretch happens, the motion takes up that stretch and maintains a more constant tension on the slack side of the belt so that you don't get into that slippage problem.
So you said this earlier or alluded to it. So comparing the two, if you have a screw take-up type conveyor system and a fixed take-up pulley, once you start adding load, then the tension on the drive pulley is going to vary with the amount of stretch in the drive,
Correct.
The belt.
And your slack side tension, yes.
And your slack side tension. So that's the important distinction, is with those manual take-ups, once you're in operation and you load the conveyor and you unload the conveyor, the tension on the drive is varying to a degree.
With the amount of torque and then the loss of tension on your slack side.
Exactly. Specifically speaking of the slack side, because of belt stretch, that slack side tension is varying to a degree.
Correct.
And then in comparison to an automatic take-up, as you described, now your take-up pulley is moving with the belt stretch, which is enabling or allowing a more constant tension on that drive pulley. So the tension on the drive pulley is not changing near so much.
Right. And to stick with that automatic theme, I mean, the reality is a lot of conveyor designers and operators will make the assumption that that tension really stays constant no matter what. The reality is there's a lot of ways that you can get variability in the tension from an automatic take-up also. One of the most common is just if you have a pulley and a weight under it, it usually is going up and down on some slide rails or some guides. It's easy for those guides to get contaminated, or to somebody hits it with a mobile machine and bends one of the slides, and you can create a lot of friction in there. And so what'll happen is when that take-up goes down, the friction doesn't allow it to go back up, and it will build in tension. You take that one step further, a lot of times if there's no room to put a weight under the pulley, they'll take some wire rope and shivs and create some geometry to get a tower with a weight next to the conveyor. Now you've got friction in all of those, and they can over time become contaminated, rust, freeze up, and you can create a lot of tension that way. Other times, especially in underground, you will see hydraulic systems, and maybe a pneumatic, but usually hydraulic, with some type of a winch that will pull it back at a certain amount. And hydraulics have hysteresis in them. They can be slow to react, so if you have a fast change in like a braking situation or a hard torquing situation on a startup, your hydraulics may not react quick enough, and you can get a lot of tension variability on the T2 side. So truthfully, as a pulley manufacturer, on the automatic take-ups, when people don't put in a decent amount of safety factor for those kind of variabilities that are really going to happen in the real world, you can get into trouble where pulleys or bearings might not handle that variability.
Absolutely. And so we're understanding that belt tension plays a major role with regards to drive slip. Mm-hmm. And we have, a lot of understanding about the minimum tension needed to prevent a drive from slipping through SEMA. And that, generally speaking, is how we determine how much counterweight we're going to need for a given conveyor system. But now we're understanding that it's important not only to be thinking about drive slippage, but also be thinking about adding a factor of safety to those tensions developed from your counterweight when you're designing your pulleys. Because when you're looking at a normal conveyor system, most of the time you have what? A drive and 3 or 4 or 5 non-drive pulleys?
Correct.
Right?
I mean, your typical conveyor of any length with an automatic take-up often has 6 pulleys. You have a drive, a snub, 2 bends, a take-up, and a tail. So the reality is 5 out of 6 pulleys are completely seeing that slack side tension. That is their load. And there's variability like we talked about, but theoretically, regardless if there's no material on that conveyor or you've got it loaded up to spilling, the same tension and loads are on those 5 pulleys for the most part. The only one that really varies with the load is the drive. So if you don't get that T2 tension correct with some safety factor, 5 out of 6 pulleys might have a problem.
Right. And so, which brings us to the bottom line. We understand that tension is one thing that an end user can control on their own. We mentioned in our earlier episode that it's difficult to change the friction of the drive once you have it installed. It's difficult to change the belt wrap once you have it installed, but it's not too difficult to add belt tension. Like, regardless if it's a screw take-up, you can go and tighten the screws on the take-up to get more tension. If it's a gravity or automatic take-up of sorts, you can add more weight. But as you just mentioned, one of the things that you have to be super careful about is if you're experiencing drive slippage and you want to add tension to prevent your drive from slipping, what's that doing to your other non-drive pulleys, as you just mentioned?
It's increasing the load on them, and your belt and your splice and everything else.
So with regards to managing drive slip with belt tension, we understand this is one of the more common ways that we deal with drive slip issues. I would say to our audience, it's just most important that for anyone who is in a position where they need to add weight to a counterweight, or they need to tighten the screw take-ups to get more tension to prevent slip, that they do an assessment or design review on their non-drive pulleys to ensure that their existing non-drive pulleys can accommodate that extra tension.
Right, yes, and PPI has a very skilled product engineering and field engineering groups. We are there to do those kind of services, and we can do it remotely for you over the phone, or we've got the field engineers that can come in and help serve you that way. So we'd love to do that rather than make a call 2 years later about something that broke. So when you have a pulley with bare steel, it's guaranteed that as you go around somewhere in that wrap, as the belt shrinks, it's going to slip on the pulley. When we add the lagging,